This lecture will cover particle kinematics, and what we'll do is we'll apply what we've learned in special relativity to solve for the energies or masses in particle collisions or decays. So let's do some examples. First, let's start with so-called fixed target particle collisions. By that I mean, suppose we have a particle, let's say it has total energy E, that collides with another particle at rest along the z-axis. So the fixed target means you have one particle colliding with another one at rest. The first particle we can let have energy E1, and it's moving along the z-axis, so we'll say its momentum is pz along the z-axis, or the k-hat direction. And we'll let that particle have mass m1, and that's the moving particle. It's colliding with another particle at rest. We can generalize this and let that particle have a different mass m2. It's at rest, so its momentum is 0, and its total energy is just its rest mass energy, which is m2c squared. And so kind of diagrammatically, what we can say is happening, we have a particle with mass m1 colliding with another particle of mass m2. So as we smash them into each other, there's some energy in that collision, and that energy can go into mass for the final state of that collision. How can we work out these masses and energies? We can start with relativity, taking a Lorentz invariant quantity. We can take the square of the so-called center of mass energy of this collision. And that's given by the Lorentz invariant quantity S. And recall that S is the difference between the total energy squared minus the total momentum squared times c squared. And you can break it up to each component of momentum squared times c squared as you subtract off. Now here we have only a momentum in the z direction, so it's only going to be that last term that contributes. So let's go ahead and plug in. The total energy, E tot, is just the energy E1 plus the energy E2. But energy E2 is just the rest mass energy of particle 2, so it's m2c squared. So that total energy is m2c squared plus E1, and we're going to square it to make E tot squared. What about the total momentum squared? Well, that's P2, but that's momentum 0 plus Pz. So I just have Pz quantity squared times c squared. So I'm subtracting off c squared Pz squared, right? So that's what I'm doing there. But let's go ahead and expand out that binomial. So I'm going to square the rest mass energy of particle 2, m2c squared. That's going to give me m2 squared c to the fourth. I have a cross term. I'm going to get twice E1 times m2c squared. That's that cross term. And then I'm going to get this term squared. I'm going to have E1 squared. So I put the E1 squared there. And then I'm going to subtract off c squared Pz squared, as I've done there. But now I'm going to put some parentheses around the E1 squared minus c squared Pz squared, because that in itself is a Lorentz invariant quantity. And that's just going to be the rest mass energy of particle 1, because we had the energy of particle 1 squared minus the momentum of particle 1 squared times c squared. And so this is just going to be m1 squared c to the fourth for the rest mass energy squared, or the invariant mass squared of particle 1. And so that lets me replace that parentheses with just m1 squared c to the fourth. I already had at the beginning here m2 squared c to the fourth, so the rest mass energy squared of particle 2. And then I had that cross term, which involved the incident energy, 2E1 times m2c squared. Okay. If the energy E1 is much larger than either the rest mass energy of particle 1 or the rest mass energy of particle 2, or actually rather that it's larger than both of those, then we can neglect those compared to the cross term 2E1 m2c squared, and so S just becomes 2E1 m2c squared. Now that invariant mass energy squared can be used to create the mass and energies of the final state particles, because energy is always conserved. If we take the square root of S, that's the final state mass, total mass that could be created in that collision. So the total mass times c squared, that rest mass energy that can be created, is just the square root of that Lorentz invariant quantity S. So it's the square root of that expression we derived earlier, square root of 2 times E1 times m2c squared plus m1 squared c to the fourth plus m2 squared c to the fourth. So if you have a collision of one particle with another at rest, and you want to produce a number of other particles in that collision, the total mass that can be created is given by that expression for the minimum E1 that's required, minimum incident energy. And one thing to note is that that was the total mass that can be created for an incident total energy of E1, but the threshold kinetic energy for particle 1 is just the difference between the total energy E1 minus the rest mass energy of particle 1, m1c squared, and that'll be the kinetic energy 1, K1. So the threshold kinetic energy you need to accelerate particle 1 to collide with another at rest to create a total mass m tot times c squared is just this E1 minus m1c squared, where E1 you extract from this formula here. Okay, so that is for fixed target particle collisions. It's just interesting to compare that if I'm able to do symmetric particle collisions. So suppose we have two particles that collide. They each have total energy E, but they collide head-on along the z-axis. So we've prepared ourselves technologically some kind of collider. And both particles have mass m. So again, we have a particle 1, E1, with energy E1, which we'll just call E. Its momentum is along the z-axis. P1 will be Pz along the z-axis. And we have another particle 2, whose energy is also E, but whose momentum is exactly opposite particle 1's. It's minus Pz along the z-axis. So in other words, we have a situation like this. We have a particle of mass m1 and a particle of mass m2. They're going to collide head-on. And that can then be used to form, that energy in that collision can be used to form mass in the final state. Again, the square of the Lorentz invariant center of mass energy is given by this Lorentz invariant quantity, the total energy squared minus c squared times the total momentum squared. Well, what is it for this case? Well, the total energy in this symmetric particle collision is E1 plus E2 for the energy, but that's E plus E, which is 2E, quantity squared. What's the total momentum squared? Well, it's Pz minus Pz, but that's going to be 0 squared times c squared. So actually, that second term is going to be 0, right? So I cross out that term, and I just have E plus E, which is 2E quantity squared, which leaves me 4E. So in other words, the total mass that can be created in such a collision, which is the square root of S, is just square root of that, which should have had a square above, 4e squared, excuse me. The square root of that is 2e, okay? And that generally grows linearly with the incident energy. So I can get twice, if I double the energy, I can create twice the mass in the final state, as opposed to the previous example where it went more with the square root of the incident energy. So let me illustrate that with some examples. Let's do an example of collisions. And I'll take a real example, a accelerator in the US called the Tevatron, which is located at Fermilab, which is basically a short way of referring to the Fermi National Accelerator Laboratory. That ring, that accelerator, has a maximum proton beam energy of 1 TeV, 1 trillion electron volts, which is 1,000 GeV, or 1,000 giga electron volts. So what is the center of mass energy when an accelerated proton from that accelerator collides with another proton at rest? So you've accelerated one proton to 1 trillion electron volts, and you smash it into another proton at rest. What is the center of mass energy? Well, from our formula before, so we're going to safely say that 1 TeV here is much, much larger than the rest mass energy of a proton, which is only less than 1 GeV, then we can use the approximate formula that is twice the incident energy times the rest mass energy of the fixed target particle. So square root of 2 times 1,000 GeV times 0.938 GeV, which is going to give me 43 giga electron volts, 43 GeV, for the invariant mass of a collision of a 1 trillion electron volt proton with another proton at rest. Okay, so you have up to 43 GeV that can be used to create massive final state particles. But, and that's in fact how the tevatron started. It was fixed target experiments. But what if you made another ring with colliding protons in the opposite direction? What center of mass energy can then be achieved? Well, in that case, as we saw, the square root of the center of mass energy, square center of mass energy is twice the beam energy. So twice 1 TeV, which is 2 TeV or 2,000 GeV. Now that's obviously much larger than the 43 GeV. And what we've seen is that the fixed target center of mass energy, square root of center of mass energy, well, it's the center of mass energy, square root of S. That root S only grew with the square root of energy in the fixed target case, but grew linearly with energy in the second case. And that was important because that's a lot more energy, and that allows you to produce, for example, 2 top quarks, each of which have a rest mass energy of about 170 GeV. So I need 340 GeV just to make 2 of them, and you have to make them in pairs, it turns out. And you can't do it with a fixed target collision, but obviously a collider, which has 2 TeV or 2000 GeV of energy, has enough. And in fact, it was enough, and the top quark was discovered in 1995 at Fermilab. And just to give you a picture of that collider, at least an aerial view, that's shown on the left there. There is a circular collider here with a radius of about 1 kilometer, which accelerated protons. And actually, it didn't smash them just into other protons. It smashed them into antiprotons, antiparticles of the proton. The ring in the front here, front view, that's actually the first acceleration stage, and then it injected it into the main ring behind it. And there were 2 experiments, 2 general purpose experiments, CDF and D0, that studied the collisions of these proton and antiprotons. There's kind of a diagram of the accelerator chain there. And those were the experiments that discovered the top quark back in 1995. This accelerator, or this collider anyway, was in operation from 1985 to 2011. So those were some examples of kinematics for collisions, where I collide one particle either at rest or in the opposite direction, and I can figure out how much invariant mass I have. What about decays? So let's talk a little bit about particle decay kinematics. In particular, I'll do an example here where we consider the decay of one particle. It's an excited kaon, which can decay into a charged pion and a charged kaon. And we can ask, what are the energies of the final state particles in the parent's rest frame? Now, I'm picking an explicit decay here, the K0 star decaying into a K plus and a pi minus. But it applies for any particle decay, decaying into 2 others. So I have one particle decaying into 2 other particles. They can be different, each with their own masses. So you can just use those as labels to apply for any 2-body decay. Now, I'm going to solve this using 4 vectors in special relativity, which just means I'm handling the total energy part like we did before and the total momentum part kind of in one go, in one equation. And we obviously have to conserve both energy and momentum separately, which means as a 4-vector combined, those 4 vectors are conserved as well. So what I can say then is that the 4 momentum of the parent, P of the K0 star, the parent, that has to be the sum of the pion and kaon 4 momentum in the final state. That's just saying that the total energy is conserved and the total momentum is conserved. But I can rearrange the equation and solve for pk, the 4 momentum of the kaon, in terms of the difference between the parent 4 momentum, pk star, minus the pion momentum, p pi, the other final state particle. So I do it that way, and then I can square both sides. Squaring both sides gives me pk squared in terms of the quantity pk star minus p pi quantity squared, which I can expand out with algebra as pk star squared plus p pi squared plus twice the cross term pk star times p pi, where this times is a 4-vector dot product. Now, why was it convenient to do that way? What I've done is when I have these 4-vector squares, that just means that's going to give you the invariant mass squared, which is just In the case of pk squared, it's just the rest mass energy squared of the kaon, so mk squared c squared. Actually, I had divided out a c squared here in 4 vectors. And the pk star and p pi give you something similar, mk star squared c squared and m pi squared c squared. And then I subtract off twice the 4 vector dot product between pk star and p pi, which for a decay of a parent at rest, so if we consider the parents in its rest frame, and therefore the products are also measured in the rest frame, then in that rest frame, that parent's rest mass energy is just its rest mass energy, mk star c squared, but I divide by c in the 4 vector language. So it's essentially the rest mass energy divided by c, so just 1 power of c, but no momentum, no 3 momentum, no px, py, pz. Now, one of the final state particles, let's say the pion, well, it obviously has some energy, but in the 4 vector language, I divided it by c. It has momentum, px, py, pz. But I'm going to do this dot product, this 4 vector dot product of these components of the vector with those components. But 3 of those components are 0. So it's going to zero out all those components. And so the dot product only picks out the product of the 0th component, mk star c times e pi over c. And that greatly simplifies the calculation. So I have mk squared c squared equals mk star c squared plus m pi squared c squared, and then minus twice, and now picking out the 0th component, it's mk star c times e pi over c, just multiplying the 0th terms of each of those vectors. And just rearranging and solving for the energy of the pion, I can move that to the other side of the equation and then divide by 2 times mk star c. And what I'll get is that the energy of the pion, in terms of the parent's rest mass energy squared, mk star squared c the 4th, plus the pion's rest mass energy squared, m pi squared c the 4th, minus the kaon's rest mass energy squared, mk squared c the 4th, divided by the parent's, twice the parent's rest mass energy, 2 mk star c squared. So that's how I can solve for the total energy of the pion in the decay. But that's total energy, by the way, in relativity. Now, there was no reason why I had to choose just pk for what I used in my 4 vector operations. I could have put p pi on the left side, and that would allow me to calculate the energy of the kaon instead of the energy of the pion. So I'll have something very similar. I still have the parent's rest mass energy squared. I still have the rest mass energy of the particle in question. In this case, it's the kaon's rest mass energy, and then I subtract off the rest mass energy of the other particle in the decay, the pion in this case, whereas before it was the pion's rest mass energy minus the kaon's rest mass energy squared. Again, divide by 2 times the rest mass energy of the parent. So those would help me solve for the pion's total energy and the kaon's total energy. So that's what you need for these 2-body decays. Let me just point out, if you're interested in the kinetic energies, kinetic energy is the difference of the total energy minus the rest mass energy. So the kinetic energy of the pion is the total energy of the pion minus its rest mass energy. And the kinetic energy of the kaon is the total energy of the kaon minus the rest mass energy of the kaon. So from those, you can then calculate the kinetic energies of each particle. So that's important if you want to know the kinetic energies. And finally, to be explicit here, we can, for this explicit decay, again, it applies to any 2-body decay, just put in the appropriate masses for each of the particles. But if I put in the mass of the excited kaon of 892 MeV per c squared, and that the kaon, regular charge kaon, has a mass of 494 MeV per c squared, and the pion, a rest mass energy of 140 MeV, into these equations, I can solve for the total energies. For the pion, I will get 320 MeV, and for the kaon, I will get 572 MeV, the sum of which will be 892 MeV, which is indeed the initial rest mass energy I started with of my parent. So that's a good check on yourself. The total energy in the final state has to equal the rest mass energy of the initial particle when it's decaying at rest. And you can find the kinetic energies of each particle by just subtracting off their rest mass energies. So for the pion, I have 320 MeV. I'll be subtracting off 140 MeV. So I'm going to have something like 180 MeV of kinetic energy. For the kaon, I have 572 MeV. I'm going to subtract off 494 MeV. So I'm going to have be closer to like 78 MeV or something like that. Okay, so those are just some examples of how to do some calculations for collisions and decays.